leveraging the power of Uber H3 indexing library in Postgres for geospatial data processing is this, sorry, I'm just still, yeah. So, gonna talk about Uber H3 indexing, but before that, let's talk about Postgres. Like we all know it's an open source database with 35 years of active development. It can handle data at scale for your all kinds of data. And then you have PostGIS as an extension with Postgres, which can also handle all of your GIS database, right? Points, polygons, and then you have also a bunch of spatial functions inside built into PostGIS functions like doing SQL joins between points, polygons, shapes, a lot of other functionalities like extracting out vector tiles, raster tiles from creating bunch of different kind of use cases and all, lots of use cases that you can do almost anything inside PostGIS, right? So what's Uber H3? As you already know, PostGIS can handle all your geospatial data, and it also provides an indexing on top of your geospatial data, which is something called an SPGIS-T. It definitely improves your performance when you're doing a lot of spatial queries like point and polygon, comparing polygons, right? And accessing those polygons as well with H3 intersects and all those kind of things, right? So Uber H3 is complementary to your PostGIS stuff, right? It's something that is used to also index your geospatial data, but it uses something of a hierarchical grid system using hexagons to index your data, right? Its performance, or the shining part of Uber H3 is actually using when you're aggregating a lot of data, or and we'll also see like it is able to change the way you process or look at geospatial data from a geospatial aspect to something of a more Postgres stuff, like you can have like you have an index like B-tree indexes in your Postgres database, which is much more efficient. So we'll also look how we can achieve those kind of efficiencies with H3, right? And again, Uber H3 was developed by Uber, and it has bindings in Python and other languages. So this is one of the bindings that it has in Postgres as well. And also PostGIS is a requirement before you do the install the Uber H3 extension inside it, right? So again, it's complementary to what PostGIS already gives, right? So when talking about H3 indexing, this is how you will look at the world from the H3 index angle. Right? You have a lot of hexagons. Now, why hexagons? Well, they obviously look pretty. It's a lot pretty to look at, right? But that's not the only reason. We'll look why. In your standard PostGIS stuff, you take a shape and you build a lot of square boxes or blocks around it to index the shape itself. In H3, you use hexagons. Why hexagons? Again, we'll have a look at that. Okay, before that, when we look at the Earth, right, it's a sphere. But when processing a lot of data, we're talking about 2D geometries, we're talking about 2D processing of the data. In your normal setup, what you use is, different projections like 4326 and 3857, which take the sphere and put it on a flat surface, right? Because of those projections, you will also have a lot of distortions coming into your shapes, polygons, points, whatever, right? Mostly polygons, not points per se, right? And like you see those projection 4326 and 3857. They are rectangles, but you see the shapes on the north and the south. They are widely different from what they actually are when you look at them on the sphere. So what Uber H3 uses is something called a Dimexian projection, right, to create the 2D surface before it actually indexes the area of the Earth, right? Why this particular choice? Because if you look at all the points in your shape, all of them are in the ocean. They're not on the Earth. And when you open it up, this has relatively less space distortion compared to your 4326 or 3857, right? So it helped them to make like a less spatially distorted indexing stuff on with Uber H3, right? So again, this is something that is more on the academic side of things, so you might not even like need to understand. This is more like a trivial fact or fact that you just need, that is just interesting to know, right? Okay, finally, we're at the question of why hexagons and why not triangles, rectangles, or any other shape in the world, right? So, I mean, this is the reason why when you have a triangle and you're moving from one point, one neighbor to the next, to the center of the next polygon, you will have 8 triangles. You cannot read this, but this is 12 triangles, right? So you'll have 12 different neighbors for each set. And then for square, you will have 8 neighbors. And for hexagons, you have 6. So one, it has relatively less neighbors. And the other amazing thing is that for all the neighbors, you move between edges, right? So this helps you simplify a lot of your moving from one neighbor to the next neighbor function. You only deal with edges and not with vertices from like the coding perspective. So that is why they chose H3, right? And yeah, that's one of the reasons. And also for aggregation, like if you're doing a lot of neighbor related queries and neighbor-related aggregations, then H3 is more helpful with that, because you know there are less number of neighbors, and moving from one neighbor to the next is relatively cheaper compared to triangles and your squares, right? Right. So taking the indexing of a point is easy, right? Because you just have one point, you put a hexagon on top of it, and that's it. You're done. But when talking about shapes, we have 2 different ways to index the polygon, right? So in this shape, you can't see it, but there are very, very small hexagons here, right? These are not points. This is not filled with a color. These are very, very small hexagons that you see here. And this is the same thing, but the inside hexagons are bigger, right? So the difference between this polygon and this polygon is that this takes about 10,663 hexagons to represent a polygon, and this takes about 901. Depending on your use case, you might want to do this or this. If you want to aggregate data over a fixed set of shapes and you want to represent that polygon in a shorter with a shorter value, then this would be the choice. But if you're comparing 2 different polygons, 2 different shapes, right? And if you're comparing point with a polygon, which you might not know where it is, right? So this would make much more sense, right? We're going to be talking about a query regarding this particular polygon, right? But this can be used for aggregating, or in specific to Postgres context, this can be used to aggregate your data and lock your data to a same vicinity, right? So you'll have less access time to that data, so you can store it closer to each other, right? Okay. So when talking about H3, you also have to realize that there is something called resolution. As we looked at the previous Earth diagram, you had bigger hexagons, you had smaller hexagons. So this is the difference between going from one hexagon to smaller hexagons, right? So this has an area of lots of 0 and 0.895 kilometer, which is really, really small for any use case, for any satellite images processing that you have. This can handle that. But in my particular use case that I worked on, resolution 7 provided a good balance between performance and error rate, right? Because so again, when you're looking at this diagram and you see a lot of hexagons, when you go to the edge of this polygons, you will have some hexagons coming out of this shape, and you will have some inaccuracy when you're talking about like on the edges, right? So depending on what resolution you choose, it will or might introduce some error rate in your geospatial data processing or aggregation. This is something to take into account. But like why I chose this for my particular use case, you will see it does not have any error rate for my particular use case, because the 7 resolution provided great performance with 0 error rate for me. But yes, it can introduce an error rate when you are indexing over when you're looking at very, very small resolutions, right? Right. So talk is cheap, right? We're gonna look at some of the things that I actually was able to implement and work with in H3 indexing. This is This is the GitHub is there, all the code is there, so you can go ahead, look at it yourself. You can try and execute all of this, right? Some of the use cases that we look at is point in Polygon, representing shapes with H3 indexes, which is what we see. Like a polygon can be represented with like a set of H3 indexes and how those H3 indexes work, right? Then the second shape that we saw, like with the less number of same H3 indexes, you can represent that. And then aggregating points to your course resolution, how that thing helps, and how we can have much faster queries in Postgres by aggregating the data points, right? Right. So for this particular use case, the right side is the screenshot from QGIS, right? I took OSM data of all of Asia, the PBF file. I think it was about 11 GB, maybe like roughly around 11 GB. And then I extracted out all the trees in Asia. And then I also got all the countries in Asia, which is about 165 countries, 165 polygons, and at about 6 million points, if I remember correctly, but something in the million range, right? And then I just want to look at what are the trees in particular countries. Obviously, this is just for demo cases. There are a lot many trees than what are there on the OSM, but this is just to have a look, just to show what Uber H3 works. This is not a data that you should be quoting anywhere. This is just to see, right? The query is pretty simple. You have trees, and then you have shapes of admin level 2, and then all you're doing is ST within whatever point is in shape, just count those trees, right? So very simple query, runs really well, takes about 38 seconds to complete, right? So again, I had a similar use case where we were doing a point in Polygon and the points were coming, like every day we had new points. So this is the use case that I wanted to solve. And then when I started looking at different indexing options for both shapes and Polygon, what I realized was the problem was not with the indexing part itself. The problem was for Postgres to handle all the geospatial functions, right? Postgres is built for indexing a lot of your normal tabular data, like string, integers, and all of that. Now, the way the same query works in H3 is something like this, okay? So you have the shape, and you have all little hexagons, and you have all little points represented as hexagons. So when you overlay on top of them, you just have to do an equal query when you're looking at which point lies in which particular hexagon. Now, this query or this table, this flat table is what is representing this polygon as H3 indexes, is not indexed. This is without index query. There is no and H3 index, when you're talking about H3 index in Postgres, it is a base 64 int, right? So if you actually index this will further go down, right? So what you're looking at when you're looking at the representation of polygon in Postgres using Uber H3 index, you will have an index and you will have a shape ID similar to it, right? And then it will be a flat table. And then you're not working, it is geospatial data, but it technically is your normal join when talking about two different tables, right? So that is why we have this huge performance benefit, because in ST within we use an entirely GIS algorithm where a ray is traced out of a polygon, and if it cuts the polygon in odd numbers, then the point is inside the shape. But in this particular index, all you do is compare the value of H3 index for your point and your polygon, and this is for resolution 7. Okay, so this query is for resolution 7. All the code is there in the GitHub. You can go and see it. But just for the slide purpose, I have made it slightly shorter, and just to cut the number of noise that we have, right? So this takes about 3 seconds, right? And again, so you will see in this hexagon, it's not sure that we have one point here. There could be multiple points inside a single hexagon, that we'll also see in the coming slides. But this makes it really fast, and even the points that have like similar H3 indexes, right? And so even the Postgres will plan the query much better than compared to a ST within function, right? If you want to look at the plan of how it sees what kind of optimization it needs to make to query the table, right? Talking about, so again, in this particular section, we are representing the polygon with a uniform H3 index, right? This is the resolution 7. All the shape has H3 resolution 7 index, but in this particular image, which is also taken from, okay, so again, this is for visual purposes. In your Postgres table, when you look at them, you will have a flat table, right? And the H3 index value would be a base 64 int, right? This is just for visualization purpose. I have created it so that I can visualize it on QGIS and how it looks, right? You have all the countries. China is missing. I don't know why. When I filtered the OSM data, maybe I also accidentally deleted some of the countries, right? So when you look at a particular shape, right? So this can be any shape. It doesn't. Oh, really? Okay. Sorry. Okay. So when you look at a particular shape, you can like represent it with a much coarser resolution, right? And when you are talking about aggregating the data for in that particular shape, and we're not comparing it with other shapes, this is something you can use to put the data in a relative similar vicinity, so you'll have much faster access time, right? Okay, so this is how the points were initially, and this is how they're separated out in H3. Okay, so you have one point representing one H3 hexagon. This is the same image but zoomed out, and just to see where the points are, right? So and yes, so when you have, so you can also create a query which is just aggregating the data at a particular level, and rather than having like joining it with a polygon, you can have your own, you can create your own maps of aggregating data at a various resolution, right? So this is also provide a much faster access time to you when you're creating maps with like aggregating maps over a particular region, right? And again, in PostGIS, I'm also using a lot of materialized view to aggregate this data, right, and refresh those materialized view. And this is again creating an H3 index for a particular point is really fast, so you don't have to worry about a lot of locks on the database itself. So you can create these multiple aggregation levels in Postgres using materialized view, and then query the data directly from the materialized view, which is again much faster. Right. More things to try. These are only the two examples that I show. I thought this would be much shorter, but it's only 5 minutes left, so I'm gonna hurry through this. Right. So again, I talked about moving to the nearest neighbor. So if your data, whatever your use case involves moving around neighbors or working with a neighbor, like a machine learning algorithm where you're talking with the neighbors and doing a neighbor analysis, like a KNN analysis, this is really good to store that data in this particular format. Right, so you can actually give your, you can actually use H3 index data in your machine learning algorithms to make like sort of a spatial analysis, right? This is another thing, edge function. So when moving from one particular hexagon to the next hexagon, you can also have directed edges, and you know, and you always know like it's going to pass from the edge. That is something that Uber used when their cabs were moving from one region to the next. Right, they knew which hexagon they were going to enter, so the analysis in that way, like whatever analysis they ran on the data, they already had an understanding where the cab is moving from which direction. It can also be used to create. You take two H3 indices and you want to know like which hexagons you want to go through. Yes, and another thing is, again, I mentioned indexing. It's a base 64 int. H3 is represented as base 64 int, so you can use your traditional Postgres indexes on your H3 indexes. And partitioning is also something I mentioned when you're talking about data in vicinity, or you can have, or when going back to the resolution, the entire Earth, like the zero resolution, represents the Earth in 122 hexagons. So if you want to partition your spatial data into different tables, then this again can be used. And also it can be used for your smaller images like continent-wise or country-wise. If you want to partition your data, this again can be used for that. right? Applications already using H3, Kepler GL, PyDex. This is just I wanted to mention. If you are familiar with these applications, they already use H3 indexes, right? These are all the sources I used for creating all the slides and all the data that you see here. And that's it from my side.